This is Programme 8 of VideoTel series on practical marine electrical knowledge. This programme highlights recent advances in electric propulsion, together with high voltage operation, safety and testing. There are many system variations around, so it's most important that you familiarise yourself with the components of the electrical system immediately you join a ship. Pay particular attention to the layout of the emergency switchboard. This study will pay dividends during a blackout or when troubleshooting the cause of a major breakdown. A growing and important development in modern shipping is the use of electric motors as the principal means of propulsion. At present, this is almost entirely diesel-electric propulsion. But in the future, it's likely that gas turbine electric will become popular as well. In addition to propulsion, especially in the cruise liner sector of the market, there are many other services which utilize the generated electric power. Power is needed for the hotel areas, for passenger comfort, for entertainment, for the lifts, the galley, the air conditioning plant, and telecommunications. A ship with such comprehensive requirements in effect houses a central power station which must be able to meet the varying demands whilst maintaining the supply voltage and frequency constant. So, in contrast to the average ship requirement of 1 to 3 megawatts, a modern cruise liner supporting comprehensive hotel facilities might require more than 40 megawatts. This necessitates high voltage power generation to reduce equipment size, current size and fault levels. Here the power is generated and distributed at 6.6 kilovolts, stepping down to 440 volts and 220 volts for auxiliary and support services. Some specialist vessels generate power at 11 kilovolts. High voltage operation necessitates extremely rigorous safety procedures, which you cannot ignore. When investigating any fault or when doing routine maintenance, it is essential that the correct documentation is filled out and countersigned. For instance, good practice would require the Chief Electrotechnical Officer, or CETO, to fill out a permit to work order for a routine insulation test on a high voltage circuit. This would include circuit details and a risk assessment listing isolation points, site preparation and personal protection sections. The electrical work permit request must be countersigned by a senior authorized person, usually the chief engineer, and the duty watchkeeper. An electrical isolation certificate is issued listing where the HV circuit is to be switched off, isolated, locked off and earthed, and in which lockout box the isolation keys have been deposited. The CETO now collects keys from the lockout box and a number of isolation warning tags and safety notices. He and his assistant proceed to the relevant circuit breaker. It's important to fix notices to warn all colleagues of the work being carried out. The circuit breaker is isolated by firstly switching to the test position, then opening the cabinet and removing the auxiliary umbilical connector, and then by manoeuvring the breaker out on its truck. The circuit is confirmed dead using the high voltage test prod. Firstly, it is checked for correct operation using a special test unit. Note that this check must always be performed before and after using the HV prod. The prod's earth lead is connected to a point in the cubicle, and the individual phases of the circuit are tested with the prod and confirmed dead. Don't forget that the prod must be rechecked for correct operation after the test has been performed. When satisfied that the circuit is dead, the cubicle shutters are locked off and the CETO attaches a label confirming it is isolated, the bottom half of which is torn off and attached to the permit to work. The circuit breaker is pushed back into its enclosure to guard against any ship movements. The circuit earth switch is now closed onto the outgoing circuit. At this point, the isolation certificate can be completed and the sanction to test filled out. Now the CETO proceeds to the high voltage equipment he needs to test. Again, the HV prod is used to confirm the circuit is dead. Portable earth leads are connected to each phase to form a local additional earth connection for operator safety. The 5 kV insulation resistance tester is now connected, while the additional earth is still connected. Firstly, it shows 2 good earth points. Then it is connected from one phase to earth. Now the additional earth leads are removed, leaving the IR tester still connected. Back at the circuit breaker, the main earth is also disconnected. And now the insulation tester measures between the phase and earth and shows a healthy IR value. The circuit breaker earth is reapplied. The additional earth is reconnected to the 3 phases for operator safety, and the IR tester is disconnected. This process will be repeated to apply the IR test from the other 2 phases to earth, and then between each pair of phases. After all tests and other maintenance tasks are completed, as listed on the permit to work, the additional earth leads are removed, first from the phases and then from the local earth point. The panel doors are closed and locked and the warning signs removed. The circuit breaker tags will also be removed and the locks returned to the lockout box. The circuit breaker earth is now disconnected and the circuit is now available for normal service. The sanction to test, isolation certificate and permit to work are now completed, signed off and cancelled. Power generation starts with the diesels. Each diesel engine has its fuel input regulated by a Woodward electronic governor to maintain constant speed in order to obtain constant generator frequency of 60 Hz. The main 6.6 kV switchboard will be separate from the engine control room. Here are the 6.6 kV bus bars and the main protection relays. These protection relays continuously monitor critical operation levels such as currents, voltages, earth leakage, unbalanced loading and temperatures, and where necessary give an alarm and trip a main circuit breaker. The breakers will be of the air type or the more modern SF6 gas-filled type, or even the vacuum interrupter type. Also in the 6.6 area are the generator AVRs, automatic voltage regulators, the synchronizing panel, and the propulsion motor excitation control units. With so many varying demands on the power supply, it is essential to have a power management system, PMS, to control its distribution and to run the power system efficiently and safely. There are situations, for instance, where it is permissible to limit propulsion load to maintain full power to the hotel services. Typically, the system sequences the generators evenly and runs individual generators at a high load factor for maximum fuel economy. It is a totally automated system which can be overridden by the chief engineer. The main use of the generated power is obviously for the ship's propulsion. During the start-up procedure, the ship's propulsion motors and auxiliary services are made ready for sea from the engine control room, or ECR. The bridge requests transfer of control to the wheelhouse and bridge wings prior to sailing. From this point, the bridge commands are repeated in the ECR and in the 6.6 kV switchboard area, where it is called local control. Control of propulsion can be transferred back to the ECR if necessary. Once a ship is fully underway, a common practice is the synchrophasing of propellers. This particularly applies to cruise ships, where it's desirable to reduce hull vibration to a minimum, and this is largely achieved by synchrophasing the two propeller shafts with the blades set at the optimum relative position. To achieve synchrophasing, the two shafts' turning speeds must be within 5 RPM. This procedure is not used in heavy seas, where the propellers might emerge from the water, causing excessive speed fluctuation. One of the main benefits of electric marine propulsion is that the diesel engines driving the AC generators and the propulsion motors do not have to be in line, allowing a greater flexibility of layout and a saving of space. As we've seen, the diesels can be sequenced for maximum fuel economy, so it would be unusual for all four to be running together. At the non-driving end of each propulsion motor are housed the shaft speed and position pickups. These provide essential information to the power management system and are crucial in defining the position of the rotor for pulse mode operation at very low speeds. Marine propulsion motors are almost universally AC. In some cases, the chosen configuration is induction motors running at constant voltage and frequency, linked to controllable pitch propellers. Some specialist vessels, such as cable layers and offshore drilling rigs, may use DC motor drives, but their power capability is limited by the low-voltage rotating commutator, which requires increased maintenance. A significant modern development is the use of variable speed drive technology. This entails the use of static converters feeding variable frequency AC to synchronous motors driving fixed pitch propellers. Because all the equipment on the propulsion side is operating at high voltages, an interlocking key system is in place to ensure that each unit is properly earthed and disconnected before access can be gained. Again, a permit to work and isolation certificate would have been completed, and circuit earthing would have been applied before entering the high voltage area. Power from the 6.6 kilovolt mains is stepped down to 3 kilovolts by the propulsion transformers. Each converter is fed from a separate propulsion transformer, one wound star-star and the other wound star-delta. This combination assists in the reduction of voltage harmonics on the 6.6 kV supply side. The converter is the equipment which converts a fixed frequency input, usually 60 Hz, to a variable frequency output, for example 0 to 29 Hz, which will drive a 24-pole synchronous motor at between 0 and 145 revs per minute. The converters use fast-acting semiconductor switches called thyristors. A thyristor can only conduct current in the direction of anode to cathode. This will only occur when the anode has a positive voltage relative to its cathode and a trigger pulse of current is injected into the gate terminal. A thyristor cannot be turned off by a gate pulse. This only occurs when a current falls to 0 and its polarity is reversed. This happens automatically on a 3-phase AC supply when the current is diverted to another thyristor. A perfect switch has no power loss, as it will have 0 resistance when closed for current flow and infinite resistance when open. A conducting thyristor develops about 1.2 volts between anode and cathode, so when carrying, say, an average current of 1000 amps, the power loss is 1200 watts. This heating effect is rapidly dissipated by a finned aluminium heatsink to avoid thermal breakdown. Further cooling effect is obtained by forced airflow over the heat sinks or by direct water cooling through ducts in the aluminium. Water purity is important, and its conductivity is measured in microsiemens. Frequency converters can switch as AC-DC-AC, the synchroconverter type, or AC-AC, known as cycloconverters. This is a three-phase synchroconverter. It takes fixed frequency AC and under computer-controlled switching converts it to variable frequency AC and changes the motor voltage in proportion. The converter is in two identical sections: the network bridge, essentially the controlled rectification stage, and the machine bridge, the controlled inversion stage. The bridges are connected by the DC link reactor coil, which provides a controlled current source to the inverter stage. This is housed and cooled separately. The variable three-phase output is fed to the motor. Computers control the converters. There is one computer per propulsion motor. To ensure smooth running and to have built-in redundancy, there will be 3 computers available. The third computer is online and tracks normal operations, but to ensure that it will cope with handling the propulsion on load, it will be regularly switched into service. To achieve this, the power supply to the propulsion motor has to be switched off before the changeover of the computers. In a synchronous AC motor, the rotor magnetic poles are locked in synchronism with a rotating magnetic field produced by the three-phase stator windings. The stator field rotates at a speed given by N equals F times 60 divided by P, where N equals revs per minute, F is the frequency of the three-phase supply currents to the stator, and P is the pairs of poles arranged within each stator winding, the same as the number of rotor poles. The variable frequency from the converter directly fixes the rotor shaft speed. The required shaft torque, T, is proportional to flux and current, where I is the stator current and phi is the rotor magnetic field flux. The direction of the stator field rotation is set by the sequence of currents supplied to the 3 stator windings. To reverse shaft rotation, the propulsion computer will bring the forward speed to a controlled stop, then switch the converter thyristors into a reversed sequence. The propulsion motors have 2 separate 3-phase stator windings fitted 30 degrees apart. This arrangement creates a 12-pulse torque to reduce shaft vibration. In an emergency, it would be possible to run as a half motor with reduced power output, but the 6-pulse operation will increase vibration and voltage harmonic disturbance. Each half motor is fed from a separate converter. A synchronous motor has field poles mounted on its shaft which lock into synchronism with the stator rotating magnetic field. The rotor field requires a DC current to magnetize each pole to the required strength to produce the shaft torque. The DC field current is obtained from a small shaft-mounted rotary AC exciter, also called a rotary transformer, which supplies shaft-mounted diodes. This is called brushless excitation, as no moving contacts are used. The AC supply to the exciter uses an AC-AC thyristor controller. There is a spare excitation unit which can be switched to replace either the port or starboard unit. At normal speed, a synchronous motor produces an internal back EMF in the stator windings which acts to automatically assist commutation of the inverter thyristors. However, at very low shaft speeds, 10% of normal or less, The back EMF generated is too low for this purpose. In these circumstances, the thyristors on the network bridge are switched to briefly suppress the current in the DC link, allowing the machine bridge thyristors to turn off and regain control. Thus, at low speeds, the motor is effectively kicked round by the application of discrete current pulses into the stator phase windings. This pulsed mode operation requires encoders on the end of the shaft. They sense the actual position of the rotor poles and ensure that the DC link current is directed through the machine bridge thyristors to ensure shaft rotation and direction at low speed. The use of current switching converters has a penalty: the introduction of voltage disturbance harmonics into the main supply network. These harmonics may result in other circuits and equipment malfunctioning or overheating. The dominant harmonic frequencies are 5, 7, 11, 13 and 17 times the 60 Hz supply frequency, and the size of the harmonic voltages are approximately the reciprocals of those numbers, i.e. 20%, 14%, 9% and so on. Here we see the AC supply voltage has harmonic disturbance, showing as small spikes on the sinusoidal waveform. This is because the propulsion is running without harmonic filters, which have tripped out due to a fault. The harmonic filters are circuits with very low impedances which are tuned to the troublesome harmonic frequencies. The filter action is to absorb unwanted harmonic currents caused by converter switching. In order to locate the fault, strict safety procedures must be adhered to in high voltage areas. An electrical permit to work is filled out by the electrical technical officer and countersigned by the chief electrical technical officer, the chief engineer, and the senior watchkeeper. Only when all the signatures have been obtained can the ETO and the CETO, and for safety they must work as a pair in the 6.6 kilovolt area, begin to investigate the fault. Firstly, they disconnect and isolate the relevant breaker. This one is of the standard air brake type. The panel door is closed again, and a safety note is hung in a prominent position. At the back of the cabinet, the cable is connected to earth through an earthing switch. This process releases a trapped interlock key, which is then used to gain entry into the filter room. In the filter room, a temporary earth is applied for a few minutes to ensure full discharge of the harmonic capacitors. Then the individual capacitors are disconnected and tested. 15.6 microfarads is the expected reading, whereas this capacitor is out of tolerance, showing 20.8 microfarads. When it's replaced, the waveform will return to its spike-free appearance. Of course, in addition to 6.6 kilovolts, there are circuits running at 440 volts and 220 volts. The main 440 volt switchboard is sited local to the engine control room. There will be substations at strategic positions around the ship, stepping down the voltage for use in such areas as the galley, the lifts, and the air conditioning compressors. Electrical circuit equipment requires special protection relays, which are usually fitted on the front panels of main and sub-switchboards. Periodic maintenance testing of such relays is necessary to confirm their operation and accuracy. This work requires calibrated test equipment and is usually done by outside contractors during a major refit in dry dock. The equipment injects a set current and records the time for the relay to trip. Here, the contractors are testing a 33.3 kilovolt vacuum interrupter circuit breaker. This relies on the contacts being in a very high vacuum to limit arcing on opening and closing. The test equipment applies a very high voltage between the breaker contacts to verify that the vacuum insulation is secure. Another periodic task is to check for local hotspots, and here the use of a special thermal imaging camera tells the operator where heat is being produced, for instance at a high resistance bus bar joint. The camera can freeze the image, and these still pictures can be downloaded to PC. A recent development is the introduction of special observation ports at the back of the high voltage cabinet to allow thermal observation without compromising safety. A digital stills camera provides a standard visual reference, and both kinds of image are incorporated in the contractor's report. This concludes the subject for Programme 8. We have recognized the growing application of electrical propulsion for ships and how a large power requirement necessitates high voltage power generation. We've seen the attendant rigorous HV safety procedures. We've described electric propulsion technology which relies on the action of thyristors within computer-controlled frequency converters. We've reviewed the operation and control action of synchronous motors and described how pulsed mode operation is required at low running speeds. And we followed a fault-finding procedure to locate a problem within a high-voltage harmonic filter. Finally, we examined the testing techniques for protection relays and showed the monitoring of operating temperatures of live electrical equipment. We recommend that you watch this program again and that you consult the book Practical Marine Electrical Knowledge, which accompanies this series and will allow you to study certain aspects in greater detail. Finally, here's a list of contents for all the programs in this series.